Um, so I'm Ed May. Nice to meet everybody here. Glad to be with you all. I'm a CPHC in Brooklyn. The agenda for today is pretty short. Maggie and I are going to talk a little bit about the house, the project that we've done here, and then we'll try and leave some time for questions at the end there. But basically, we'll sort of cover the intent of the project, where it sort of comes from, the Marshall Fire challenge, the neighborhood, and then we'll dive into some of the nitty gritty, the building itself, how it was put together, the materials, the systems, whatnot. And of course, as I said, we'll leave some time at the end there for questions. So as I said, my name is Ed May. I was, back in the day, a builder. I was an architect. Nowadays, I practice exclusively as Passive House consultant and an educator. And so all we do in our office is Passive House work. I am based out of Brooklyn, New York. It's where you find me at the moment. And all we do, as I said, is help other teams achieve their Passive House goals when it comes to their projects. So we work with builders and architects and homeowners, developers, all sorts of different teams that are striving for one reason or another to achieve the Passive House standard for their project. And as I said, we kind of or we sort of work across the range of different issues and items pertaining to Passive House. So that's everything from thermal bridge simulation to detailed building modeling. Of course, I was a builder, and so I spent a lot of time on job sites. Nowadays, of course, I sit mostly in front of a computer, so I spend a lot of time writing code and building computer programs to help us do what we do better, faster, simpler, and smoother.
So I'm here representing Shape Architecture Studio. We're a small 8-person firm out of Denver, and we do a lot of high performance design. That's kind of our specialty. It's kind of been integral. It's at our core of our ethos at Shape. We do a bunch of projects ranging from residential to prefabricated to small sort of boutique projects like nature centers or hospitality. And we try to bring Passive House principles to all of them. In fact, a little known fact about us actually is that when Morgan Law started this firm in 2016, SHAPE was actually an acronym for Sustainable Habitats and Performance Engineering. So ever since the beginning, it's been super critical to us to bring good design, good sustainable principles to architecture.
Right. So let's jump right in. So before we dive into the building itself, for the benefit of those of us who are new on this call here, who maybe don't have as much familiarity with Passive House ideas, the Passive House framework, let's just take a very few minutes and talk briefly about this idea of a Passive House building and how we take a typical building and turn it into a successful Passive House building. So we're going to use 5 basic principles, 5 basic steps. And I'll just talk briefly about these, and then we'll dive into the actual project here. So first of all, insulation. And I know what you're thinking. That sounds really boring, and you're not wrong. It is not learning computers. It is not robots. It is not AI. It's insulation. That's going to be the first and most important thing that we're going to do or add to our buildings. Lots of high quality continuous insulation. It's going to work very well in summer, work very well in winter for reducing energy consumption and improving the comfort of our buildings. In addition to insulation, we're going to build our buildings airtight. And that sounds weird at first. You might think, oh, that sounds gross. Is that like one of those office buildings from the 1950s where I can't open the windows? Not at all. What it really means is that in the winter, when there's a snowstorm, you can seal up the building. When it's summer and it's incredibly humid outside, you can close up the building. It doesn't mean that you can't have operable windows. What it means is that you're in control of how the air moves through your building. So we don't want uncontrolled air leakage through the walls, roofs, floors of our building. We want to control and be intentional about how fresh air is introduced into our building. So we're going to build in this airtight manner. We're going to reduce or eliminate what are called thermal bridges. Thermal bridges, that's a weird term. Be forgiven if you haven't heard that term before. Thermal bridges are breaks, discontinuities, disruptions in the continuous insulated envelope of your building. And we're going to reduce or eliminate those through good design. We're going to work really hard to find, identify, locate, and then design out these breaks, these places where the insulation is omitted for one reason or another. It can happen for all sorts of different reasons. And we have lots of different techniques and products that we use to eliminate those thermal bridges. And we're going to use passive house windows and doors. So these are unique products, the same word, window, door, that we use in North America, but these are entirely different, an entirely different species from the types of products that we're familiar with. It's going to be very, very high quality, very robust, very thermally efficient, very comfortable, very air sealed. So they're a type of window and door which are suited for, designed for, built for passive house projects. We're going to be very careful about how we distribute that glazing around the building with an eye towards performance, comfort, solar access, what have you. So we're not going to just sprinkle windows willy-nilly. We're going to be very thoughtful and intentional about how we place those windows in our building. And we're going to use very high quality window and door products. And we can talk a little bit about that as it pertains to the sunflower house as we get into it there. And then the last of our 5 key techniques that we use to build a passive house: dedicated fresh air ventilation. Dedicated fresh air ventilation. In the United States, in North America more broadly, we have this thing that we call HVAC. We take heating and ventilation and air conditioning and we smush them all together into one system, and we don't really think too much about it. We design the building and then we throw some HVAC at it. In passive house world, we take a very different approach. We have a very intentional and thoughtful approach to the fresh air ventilation system on its own. So in passive house world, we separate out the ventilation from the heating and the air conditioning, and we design in good fresh air ventilation from the very beginning. The fresh air ventilation is, of course, important for the people who live in the buildings. It's required for a healthy and comfortable interior environment. And so we're not going to apply that as a layer at the very end. We're going to think about ventilation from day one, and we're going to bake that into the design of our buildings. And then lastly, we're going to complement all of those passive strategies with a very efficient heating and cooling system. In most cases nowadays, we're going to strive for what we call electrification. That's primarily for energy efficiency reasons, but we can use and do use any type of system under the sun. For passive house buildings, there's no restriction or requirement on the types of equipment, but we're going to try and be as efficient as possible in our heating and cooling. And again, we're going to try and think about that from the very beginning. We're going to think about all these comfort and performance attributes of our buildings from day one in our design, rather than layering them in as additional elements at the very end. So that's just a super fast primer on passive house. But now I'll turn it back over to Maggie, and she will tell us a little bit about the actual project we're talking about here today.
Yeah, so we'll start from day one, because that's where the design started. Like Ed was saying, passive house was ingrained from the beginning. So this is our site pre-fire. This neighborhood was unfortunately devastated by the 2021 Marshall Fire. And so these were the site conditions before. You can see that the house faces mostly south, skewed a little bit to the east, which was an important consideration for us as we got into the design. And these were our after photos. So this is the site that we were working with. This is what every property looked like in several neighborhoods. The photo on the left is from our very first site visit to the property with the owners. And as you might imagine, this became a very emotionally charged project for us. I do want to point out one of the owners is actually on the call today. So hello, Kevin. It's great to see you. So seeing these, it does beg the question, because there was a huge rebuilding effort after this fire. And so a lot of these folks decided to rebuild passive. So begs the question, why passive house? And there's a number of reasons for this, but I think really in part it's because passive house also takes into consideration a much larger underlying issue in the building industry, which is just general climate instability and growing unpredictability. That fire was a testament to that. And it really makes it so clear that there's a need for resilient structures to provide sanctuary and stability and peace of mind, given a somewhat shaky future for this earth. And so we can think about how each of the passive house principles that Ed was just talking about contributes to that stability, especially in places like the Midwest and Colorado, where air tightness and mechanical ventilation really helps not only with overall improved mechanical performance and reduced mechanical footprint, but also resist permeation from wildfire smoke. That's almost a constant in our environment. High performance windows optimize solar gains in high altitude conditions where the sun is super strong. And super insulated assemblies provide that extra buffer for those dramatic temperature fluxes that keeps your indoor comfort consistent. So our clients, Casey and Kevin, were hugely instrumental in this process for us, and we're so motivated to pursue passive house from the get-go. Even when we were doing these site sketches, we had a lot of flexibility to really prioritize those design moves that would make this house low impact and high performance. So this is an image of that initial site concept that we kind of just ran with, actually, for the whole design process. So as you can see, like I said before, it's south facing mostly. And in Colorado, we find that typically the heating load for these houses is greater than the cooling load. So the more we can give that heating burden back to the sun, the better. The owners also really wanted to maintain a connection from their front yard to backyard. They have 2 young kids, and maximizing that outdoor space. And in general, just maximizing outdoor living spaces was a really important component of this site placement and the site design. And with that, just providing gathering spaces inside and outside that took advantage of some western mountain views. It was also important to the owners to have sort of a similar square footage to their previous home. So we started with just a very simple rectangular geometry to optimize the surface area to volume ratio, and separated the garage, this is the garage here, from the thermal envelope completely to simplify things. And then from there, our process was kind of just making small adjustments to improve the performance of certain elements, like roof orientation or window and door overhangs, and even adding like shade trellises. So Ed and BLDtyp played a huge part in this for us. There was an immense collaboration there that we could not have done it without them. They were involved super early on, and literally we sent them sort of a schematic model of the design of the house, what we were thinking. And literally Ed put together an extremely comprehensive energy model just from that sort of schematic assessment, where he was able to then make recommendations based on the climate zone and heating and cooling loads and site placement even, and also recommendations on which passive house performance target we should be aiming for, which was in this case the PHI low energy building, and how to improve overall performance. In fact, I think even the metal overhangs that you see on some of the windows were calibrated dimensionally by Ed in his modeling to reduce unwanted solar gain in the summer and keep it in the winter. So just to super quickly take you through the layout, this is the entry level. And in this house, this is also technically considered the basement or the lower level. The red line denotes the thermal envelope here. And this floor houses mostly guest bedrooms, offices, one of which I must add can only be accessed by a secret bookshelf door. A North Face art studio, and most notably, a very small mechanical room in this area that was able to house all of the mechanical equipment required for this house. So going up a floor, this is kind of the main level, which contains the primary gathering spaces. We have an open floor plan, KDL, kitchen, dining, living room, which with some strategically placed south and west facing windows openings. And for us, this was important, again, to capitalize on those mountain views, but also to be able to start calibrating that solar heat gain. We also ended up doubling the livable space with the outdoor roof deck above the garage, which again was completely outside the thermal envelope. So then this is the upper level, 3rd floor, and it was where we housed all the bedrooms. And as you can see, it's a super simple geometry. It is, very lean, and we were super intentional about that. I think the conditioned floor area is about 2,600 square feet divided between 3 floors. So fairly compact and strategic that way. And I'll hand it back to Ed.
So that's a great introduction to the project, Maggie. Thank you for that. So as Maggie said, our office was involved from the beginning, and I thought what we could talk a little bit about here is just some of that process. Let's say that you really do want to get a certified Passive House building. How does that go? What does that process look like? And then, of course, we'll talk a little bit about some of the specific materials and some of the equipment that we used in the project there. But as Maggie alluded to, if you're striving to achieve one of these Passive House goals, it's important to fold in the modeling and assessment in the earliest stages of the project. Maybe not at day one. You want your architecture and your site plan to be about the site and the architecture, not necessarily about the model. But pretty quickly, you want to move into a phase where you're assessing and quantifying the performance of your building in all of its various aspects. And importantly, one of the things that we recommend is that you don't simply model a single version of your building, but you model across a range of options. And so especially in the earliest stages, this is a slide from a assessment report that we do as a standard for early phase projects, where we model the building that you showed us. You sent us some drawings, and so we model up that building kind of the best that we can. But then we look at, well, what would a sort of code minimum version of the same building look like? What would a version that had, in this case, a sort of semi-improved insulation envelope? What would a version that had a really good mechanical system look like? And then what would sort of fully kitted out Passive House versions of the same building look like? So we're always looking across a range of options. We're never modeling a single variant or version of the building. We use the tools to model lots of different options at the same time to make sure that everybody has the right context in order to make good decisions about the project and about certification. And so what you're seeing here is just an example of how we might approach that. These are some of the results from some of that early phase modeling that we might do. What we found in that model was that the PHI low energy building certification was a good fit for this particular case. So one of the things that we recommend that you do in this sort of early sort of design finding phase is you stress the building, try the building in a variety of configurations, and don't settle on a single certification right away. Sort of look and see what's a good fit for the building and try a few different ideas. In this case, the low energy building certification seemed to be a really good fit. It was a good balance between the glazing, the summertime overheating performance, the shading, and the insulation levels. And so you can see some of the sort of target levels here for the R values and the windows that we ended up with as a result of this early phase modeling, where we were kind of looking across a range of different options there. And these kind of values would be typical for a building like this in a climate like Louisville, like an R30 floor, R40 walls, R50 roof, that kind of thing. Somewhere in that range is sort of to be expected in this climate. That'll vary, of course, by different climates, but in that climate. Now, once we get through that early phase modeling, once we kind of have a rough idea of where the building stands, and we've worked with the team to make decisions about, okay, we're going to target this goal, not that goal, we can then dive into a more detailed assessment modeling, where you take a very specific single version of the building and you model it to a very high level of resolution. So you're going to model every stud and fastener and whatnot. And what you can see here are just some examples of the specific assemblies that we ended up recommending for this project. This project heavily relied on a dense pack cellulose insulation, and you can see some pretty thick cavities here. On the left is the exterior wall, and that's a double stud wall. If you're not familiar with that, it's just a regular wood stud wall, but instead of just building one, you build two, and then you separate them and you fill the space in between with insulation. It's very easy, low-cost way to build a very thick wall. In this case, I think we had about a foot of insulation there in the walls. And then on the right-hand side, you can see the roof insulation in the roof cavity. And then really interestingly for this project, on the bottom there is the concrete free floor slab. So a concrete free floor slab, that done for all sorts of different reasons. But that's a technique where you just lay down the insulation. The blue in that diagram there is an insulation foam. And then on top of that, you put several layers of plywood. So you're able to fully eliminate the plywood the concrete in an assembly like that. So these were the assemblies that we ended up with for this particular project. In terms of the mechanical system, so I was saying before that we want to approach the mechanical system very intentionally and thoughtfully from the very beginning of the project. And in general, what we recommend is that we split apart the heating system, the cooling system, and the ventilation system. So rather than having one thing called HVAC, we have multiple different systems. Because in fact, those different systems have different logics, different rules, different requirements. They do different things in the building. The fresh air ventilation system is responsible for keeping the people healthy in the building, whereas the heating system and the cooling system are responsible for keeping the space comfortable. On the left there, you can see the air source mini split heat pump system. And so that's what you're seeing in the mechanicals, this photo from the mechanical room on the left-hand side there. So that's a system which is dedicated to just recycling the air in the building, heating it up in winter, cooling it down in summer. On the right-hand side, it's a little hard to see, but way in the back on the right-hand side, there's like a box with a bunch of kind of spaghetti tubes coming out of the top, ducting coming out the top. That's what's called an ERV, an energy recovery ventilator. You can think of that as the lungs of the home. That is not part of the heating system. It is not part of the cooling system. Its only job is to bring fresh air into the building 24 hours a day, 365 days a year, to filter that air and then distribute that air into the home. At the same time, it's extracting stale air out of the building. So it's taking contaminated or stale air out of bathrooms and kitchens and mudrooms and project rooms and getting that out of the building. And again, it's not part of the heating system. It's not part of the cooling system. Its only job is to make the home livable and healthy for the occupants. So that system's going to run all day, every day. And of course, we're using a heat and energy recovery core in that piece of equipment in order to do all of what I just described in the most efficient and comfortable way possible.
It's also worth noting too, while we're on these photos, I was just thinking about it, that during construction, when these photos were taken, the entire house was heated with basically one of these little heaters that you see, these portable heaters. So super airtight, super insulated, really good.
That's a good point, Maggie. Yeah, absolutely. So as I said, once we get into this kind of like later level of design and assessment modeling, we're going to go to a very high level of resolution. So you would not do this type of work in the early phases of project assessment and modeling, but by the time you get to construction documents and you have a very clear target for your certification, you're going to get into things like thermal bridge assessment. And as I said, thermal bridges, that's a weird term. It basically means anywhere that you have a gap or a break or a discontinuity in the insulation of your building. And that can happen for all sorts of reasons. It happens for structural reasons, happens for aesthetic reasons, happens because you go from a big fat wall to a narrow little window. Those are very typical sites of thermal bridging. The problem with thermal bridging is, well, there's several different problems, but let's say the two key problems are you lose a bunch of extra heat in the wintertime. So you have excess heat loss that drives up your energy consumption. But also, as a result of that heat loss, you sometimes get left with cold surfaces. And cold surfaces are where you can see moisture problems, mold problems, mildew problems. So this type of assessment modeling that you're looking at here, where on the right-hand side, we take the window detail and we run it through a battery of different simulation tools to see the temperatures under different conditions. We can use that type of modeling to make sure that we don't have any sort of mold, moisture, cold surface problems in this climate. So we can effectively design out those types of moisture issues from the very beginning. So again, on the right-hand side, what you're seeing is the temperature of that assembly under certain conditions. And we can predict, therefore, whether or not we're going to see some type of mold, moisture, mildew issue. Now that's good and that's useful and that is excellent so far as it goes for those types of kind of two-dimensional details like a window or a wall-to-wall, those kind of details. With this particular project, there was in fact some structural steel that needed to be used for structural reasons. And that led to what are called three-dimensional thermal bridges. So this gets often a little bit off into the weeds, but we thought it was interesting to share because it was one of the challenges of this particular project. So when you get into these types of junction details, where maybe you have like a T shape of steel, then you have to go into a whole different world of engineering assessment software. We're still kind of fundamentally looking at the same things. We're still fundamentally looking at the rate of heat flow, and we're looking for those cold surfaces and risk of mold or moisture. So we're still looking at the same criteria, but we're going to use a different set of tools in order to do that type of modeling. And so this particular project had a few instances where we had that type of structural steel that we had to wrestle with and design in a way that allowed us to be confident that we wouldn't have any of those issues around high heat flow or mold or moisture damage. And so what we use in that case is a three-dimensional thermal bridge simulation tool. It's basically the same tool that we were looking at or talking about before, where we're modeling heat flow through an assembly. But in this case, rather than doing it through like a flat slice of the building, we can actually do it for an entire 3D detail. So we build up these details and bring them into these specialist tools. And this is all in metric, but the takeaway here is that we don't, even with this structural steel, we don't have, in this case, any low temperatures, any mold risk, moisture risk, risk of thermal discomfort. There is excess heat flow, but not to the level at which it causes a problem or causes any sort of issues with the interior environment. So again, what we're trying to show here is just that we have tools to do this type of assessment. You don't need to invent these tools. You don't need to kind of go by rules of thumb or guesses. You know, these tools exist. They are part and parcel of what it means to be a passive house practitioner these days. And so, you know, you can deploy these tools on your projects in order to solve these issues, in order to make sure that you're building the most comfortable, durable house that you possibly can. And then lastly, Kevin shared this data with Steve's office. And so we thought we would show it here because it is really interesting. This is some monitor data from the home. And one of the most interesting things that we see here, so the green bars are energy consumption of the heating system. And this is in what, October, early November. And you can see there that the heating kind of goes along really low and then kind of goes up and then comes back down. Well, what happened there where it went up? And it turned out from what Kevin said, that was a weekend when the family was away. So there's actually a period where they were not at home. What this shows us, what this demonstrates to us, is the way that these buildings act as, let's call them thermoses. So any bit of heat which is released inside the home from people, right? We release about 100 watts sort of resting, to lighting, to cooking, all of this heat, which is released by the things that we do, stays in the thermos. But when nobody's there to run the lights, run the heating, release the body heat, you can see that the heating energy actually does go up there, which is exactly as you would expect, right? These buildings are designed to operate with people in them and to sort of store all of that excess heat, and that allows us to drive those heating loads way down. So this is a really interesting example that shows the performance of the building acting just as we would anticipate.
So these are just some section drawings that were taken from our construction set. And you can kind of see, it's probably hard to see, that there's some markups on them. And basically that's our builder, whenever this project started construction, was super involved as well in the process of figuring out, in this case, you know, how to physically, run our air and vapor barrier through all of these different assemblies that Ed was talking about. And so this is kind of we thought, a poetic way to describe that is just that, we have all these details, and our builder had a meeting with, I believe it was 475, and us, and literally just walked through every single one of these connection details to figure out the construction sequencing to make it actually buildable. Because while, you know, the building has relatively simple geometry, it was still a team effort in figuring out how, you know, even at this like this overhang, for example, how we had to run the air and vapor barrier up and then on the underside of an exposed floor and then back up the wall, how to sort of like make that work became a really big question for this project. And so, yeah, Ed was involved in that process as well. It really took a village. But basically, I think our process as far as like the drawings go, I can speak to that a little bit, was just, really not taking anything for like, like the final answer. Like we really wanted to have everyone's input on everything to the maximum extent possible. And I think this drawing shows that. And likewise, this is sort of another example of that, sort of a finer grain, taking some of our details for our windows in particular, and actually applying specific products to these areas, because what we found in a lot of these cases was that we had very unique details for each assembly and each window type, even depending on where these details were in the building. And so figuring out, where the adhero goes and how it all laps together over a double stud wall, which is a little more complicated geometrically, was a big exercise for us. I think it's funny too, also, the first thing you see on this page is a markup that says, "This seems wrong," from our builder, just because, like I said, it's really like nobody has all of the answers. The team has all of the answers, and us with 475 and with Ed and with Livingcraft, the builder, together we were able to make this happen. So these are some construction photos. The house was constructed between, I believe, April of 2023 and March of 2024. So here's some photos of that. You can see on the left at the top that slabless slab that Ed was describing earlier. This white is starting to be the 10 inches of foam, and then 2 layers of plywood, and then the finished floor above that. And then on the right here, you can see them. I think they're installing the service cavity on the interior face of the wall and ceilings over top of the Intello to protect that air and vapor barrier behind it. And here's some close-up views of the roof. In these images, you can see that black layer, the Minto, is applied directly to the top of joists, which is, I think, probably a somewhat unique assembly. And then there's a roof venting channel above that. And high wildfire risk means that if we're doing a vented roof, we use linear vents with basically an intumescent coating that essentially seals itself up when exposed to extremely high temperatures. So, because I know it seems a little counterintuitive to be doing a roof vent in a high wildfire zone, but this way, the roof still performs extremely well with venting. We don't have to worry about doing an unvented roof, but it's also protected against sparks and embers that could potentially get sucked up into the roof. And this is the finished product.
Jump in with a question really quick. There was one, whether you could speak to the use of wood framing to address wildfire resilience in lieu of other materials. I'm not sure if you all could speak to that.
Yeah, so I think with houses, a lot of it does come down to cost and just ease of, construction, I think. But that said, there are ways to do wood frame construction where it is still resilient to fires. Now, one thing to consider with wildfires is that you could have, really the only type of house that isn't going to suffer in a wildfire is like a concrete, solid concrete sort of masonry construction. Wildfires are insane and they will destroy just about anything in their path. So we want to make these houses as resilient as possible. But if it's in the case of like the Marshall Fire, there's actually a wildfire tearing through your neighborhood, yes, obviously wood construction is going to be probably not ideal. But that said, there's precautions like these vents and like, how we didn't show in this presentation, but raising the kind of wood framing up a little bit off the ground by using more concrete on the lower level, as well as just using things like metal siding and fire treated wood. All of those things kind of add up to make things more resilient. And the truth of it is that most of the time, it's going to be like a fire nearby. And so that's what you need to be planning for. And I don't know if Ed has other thoughts on that too, but it is a complicated consideration. I don't know if that answers your question. But so this is the finished product. You can see some of that metal siding that we used. All of the wood that you see is fire treated or fire retardant treated. I think actually a bit of a fun anecdote that we like to share about this house is that actually when the owners first moved in, like the very same day that they moved in, there was a crazy storm with below freezing temperatures and super high winds, which prompted Xcel, the power company in our area, to cut power to this neighborhood to avoid potentially causing another fire due to like electric sparks igniting, on accident. And so while many of Kevin and Casey's neighbors actually really suffered and got extremely cold in their homes overnight, Kevin and Casey's house was barely impacted. They managed to stay super comfortable thanks to all the extra insulation that we put in, and those other passive house strategies that we use to keep it super airtight. And so I think it's kind of a nice testament to the integrity of the house and the team, that the very same day that they moved in, they started this process and finished it with a test of their building performance. So and lastly, and most importantly, the owners, I think, love it. They work from home and also homeschool, so they spend a lot of time in this house. So we thought we'd close with this sketch on the right that the family created, featuring themselves as chickens, I must add. Pretty early on, they sketched this in the process, and I think just because they were truly so excited and motivated to be dreaming up this house that would be more resilient and more safe than the one that they were living in after a devastating loss. And that ultimately for us made this design and the process one of the most special and unique passive houses we've ever completed. So yeah, Ed, any closing thoughts?
No, that's great. I guess, yeah, it was a wonderful project, a wonderful client, and certainly we enjoyed working with Shape and Frank's team at Livingcraft. Did a fantastic job with the construction. So yeah, it was a wonderful project to be part of, and glad to be able to share it with everybody today. And of course, happy to answer any questions if folks have any.